Okay, so the period of motion isn't constant because pi squared of t changes by 2 pi, right? And I'm just trying to decide whether to use a delta t or not. I'm just going to say right now, time for this to change by 2 pi that's supposed to be an r, increases as t increases. Okay? And that's very clear. And you should, of course, always understand the graph of your basic power functions, okay? The graph of the square root of t function looks like this, right? Okay? So if you want t, and let's do this, and this equally represents a pi square root of t function, right? All you got to do is say, okay, when t is 1, here's pi, right? Now you've got a scale that makes this graph. That's something you want to really understand, so I'll try to get across to pre-calculus students in case any of them ever get to the point where they can actually do this. Okay, so I'm just going to put 1 and pi here just to illustrate. And we'll call this y versus t. So here's pi on this axis, right? Well, if pi is here, then 2 pi is here, right? And if we project over and down, here is the period of the first motion. This is the change in t that causes y to change by 2 pi, right? Okay? It's important to be able to think in terms of these pictures. And you have to know the shapes of your basic power function graphs and stuff. And of course, if you've got a more complicated function from your calculus, you know how to graph maxima and minima and overall behavior, okay? So you can always sketch the graph of the function, but so often things are governed by very simple functions that you can just immediately draw the shape of to get a conceptual idea. You're not going to do mathematical analysis based on this, but it shows you what's going on, and this is going to show you why the period keeps increasing. Okay? And you can do it algebraically, but here we got 2 pi. Well, then here's 4 pi. Well, from here to here is another change of 2 pi. So you project out to here, and now here is the length of the second period, right? And then you can go up to 6 pi. And here's the length of the third period. Okay? So you go around, but you're slowing down, and then you go around, and you're still slowing down, and then you go around, and you're still slowing down. Every time around the ellipse takes longer. Okay? Now you can write that out algebraically, but I'm not going to do that right now. I want to get the conceptual idea that you would use in analyzing the results of this parametric equation that probably doesn't apply to anything important. But there are, there are equations of this nature that do, okay? And I wouldn't be surprised if there isn't something important, because the square root of t is kind of a fundamental thing, okay? So, if you can think between the lines of what I've said, you've got something. But if you understand this picture and how it tells you that you're going around this ellipse more and more slowly, that's a good start.